let's calculate the drag coefficient from Fluent and compare it to the Blasius result. And Fluent integrates the wall shear and pressure to find the drag force. And the wall shear will be like that because the flow is dragging the plate along. And the pressure will be in the perpendicular direction. And since drag is in the direction of the free stream, it's in the x direction, and there will be no contribution from the pressure to the drag. So the expression for the drag is the integral of the wall shear along the plate, and you have to multiply it by b, which is the depth normal to the screen. That's the depth of the plate, and it's usually taken as 1. Drag coefficient is basically a non-dimensionalized drag. So you take the drag and you non-dimensionalize in this fashion. So you have half rho u squared, that's u infinity squared from the free stream velocity, and L times b is the area of the plate. And since b is 1, it's usually not even written, and the assumption is that this drag is the drag per unit width of the plate. In Fluent, the drag coefficient is calculated in this way. So whatever drag it finds, it'll normalize it based on some reference values. So it'll use the reference value for density, velocity, and area. And the reference values are set in the reference values panel, which I'll show you where it is. So in that panel, that is A reference, that is rho reference, and that is V reference. These reference values will affect only post-processing of non-dimensional quantities. So it won't affect the drag, but it'll affect the drag coefficient. And students get confused by this because let's say, the viscosity is not right, but this is not the viscosity that's used in the governing equations. That's set in the material properties, okay? So keep in mind that you're affecting only post-processing. So let's calculate the drag coefficient. And I will go into Fluent, and I have to set the reference values first. So I'll go to reference values and set reference value for area, for density, and for velocity. All the others don't matter. Then I'll come into reports, and I will say report forces. I want the force in the x direction, which is where the direction in which the drag is acting, and I want the integration to be done over the plate. And then I'll say print. I have to make sure plate is selected, print, and over here I can see that that's the contribution from the pressure, so that's 0, and that's a contribution from tau W, and that's the same as the drag coefficient. So it's around 0.017, and let's compare that to the Blasius result, which I had mentioned earlier. So in our case, the denominator is 100 because Reynolds number is 10,000, and so the drag coefficient is around is going to be around 0.013. In Fluent, so the Fluent CD is around 0.017. Now that's a significant difference. And you can explain that by, the comparison of the velocity profiles that we did between the Blasius solution and Fluent. So if I go into CFD post and look at the comparison with the Blasius solution, and I can even zoom in a little bit near the wall. So let me change the y-axis extent to, say, 4. And so as I come off the wall, okay, a little distance, I'll see that I'm getting a higher value. Fluent is predicting a higher value for the velocity than the Blasio solution. This means that du dy at the wall is higher for the Fluent solution. And since tau w is mu times du dy at the wall, we expect tau w to be higher and the drag coefficient to be higher. And this effect will, the difference will go down as we increase the Reynolds number, because these profiles will then match better. And that's something I have verified, and you may want to. And so I will save file, save project. I will exit that, and I will exit Fluent. And then go back to my Workbench window, and I will actually save it in the WBPZ format. I go to my working folder, and I'll say, I'll say save everything, basically. And then if I go to my working folder, I should see that it's created this WBPZ file, and that's the only thing you need to retrieve your, to resume your project.